Hi, this is a lecture on circles. We'll start with some terminologies commonly associated with circles and then move on to the theorems associated with the geometry of circles. So, the collection of all points in a plane which are at a fixed distance from a fixed point in a plane is called a circle. You can get a certain sense of this definition from the way you draw circles using a compass. In a compass, basically you measure out a certain distance and then firmly plant one side of the compass on the paper and then basically use the pencil to draw a circle while maintaining the distance between these 2 points. And so you can easily see where this definition of a circle comes from. That is the collection of all points in a plane which are at a fixed distance from a fixed point in the plane called a circle. The fixed point is called a center. So this would be the center and the fixed distance is called the radius. The distance as a magnitude is also called the radius and the straight line is also called the radius. So now we'll look at some more terminologies associated with circles. Here we have a circle and anything outside this closed figure of a circle is called the exterior of the circle and anything inside the closed figure is called the interior, as common sense would have it. And the closed figure itself is called obviously the circle. So now I'll use these circles to demonstrate to you some other terminologies commonly associated with circles. Let's say if this was the center and consider 2 points on the circle and if you talk about the straight line joining these 2 points, this is called a chord. And it is known that the longest possible chord is actually called the diameter and it passes through the center. So a chord which passes through the center is the longest possible for that circle and is called the diameter. And something else that is interesting is that the length of this chord or diameter is equal to 2r. That is diameter length of the diameter is equal to 2 into radius. That is 2 times the length of the radius. That is an important property or very important parameter, so to speak, of a circle. Consider another circle in which, let's say, you have 2 points on the circle itself. Now this line segment, which is the line segment PQ, divides the circle into 2 parts. One of them is called, this part is, delete that, I should be more careful, but this part which I'm shading right now is called the major segment, and this part which I'm scribbling over right now is called the minor segment, right? And also if you basically take out this part of the circle, which is bounded by P and Q on two sides, this smaller part which will look something like this and is visibly smaller than this part, this is called the minor arc PQ. and what is left over, this large part of the circle, again bound by PQ. Obviously this is a very crude drawing, but bound by PQ is called the major arc PQ. So a chord or 2 points on the circle divide the circle into minor segments and major segments. The region inside is divided into major and minor segments, and the circle itself is divided into minor arcs and major arcs. Another way to look at how a chord or 2 points divide the region inside a circle would be to consider sectors. I'll show you what sectors are. Again, let's consider 2 points, let's say P and Q. Join P not to Q but to the center of the circle itself. And again, if this were say, sorry, point O, and now join OQ. Now this portion of the region, which I am shading over right now, is called the minor sector. This is like a piece of a pizza or something of that sort. And now the part I'm scribbling over right now, this large part, is called the major sector. So these are all the terminologies that we'll be using throughout this lecture to refer to specific parameters or entities inside a circle. Next, we'll look at the first theorem that we encounter in this lecture, that is theorem number 1. Equal chords of a circle subtend equal angles at the center. Recall what subtending an angle means. Say if you have a straight line and you have another point which is not lying on the line, then say this is PQ and if this were point O, then the angle POQ is the angle subtended by the line segment PQ on O or at O. So that's just a quick reminder of what the angle subtended by a straight line means. And so if this is the center, we need to prove that this is point O. Let's join this and name this A, B, and let's just call it C, D. And we'll join this also. Okay. So we have to prove that the equal chords, so given AB is equal to CD, we have to prove that equal chords of a circle subtend equal angles at the center. So we have to prove angle AOB is equal to angle COB. Let's see how we can do that. The proof is rather simple. Considering OD, OC, OB and OA are all simply the radii of this circle, they are all actually equal to each other. So this equal to this equal to this equal to this, and we are already given that this equal to this. And so we'll write it down in formal language. We have OD is equal to say OA and OC is equal to OB. We'll not use the fact that in fact OC also equal to OA. We'll leave it at this because all of them are radii, and we have AB is equal to DC given. I should have written this the other way around. It doesn't make a difference, but let's say this. It's the same thing. So we collect all this and say triangle OCD is congruent to triangle OBA by SSS congruence rule. This implies angle DOC is equal to angle AOB, which is what we have to prove. This is, by the way, by corresponding parts of congruent triangles. So hence proved. Let's look at theorem number 2. It says if the angles subtended by the chords of a circle at the center are equal, then the chords are equal. Basically, it can be called the converse of the first theorem that we proved. So we'll start off by joining basically making the angle itself. We'll draw the radii. And so we are given that this angle is equal to this angle. Again, let's just call it CDAB. Given that angle CO, if this were O, the center is usually denoted by the letter O. COD is equal to angle AOB. Then prove that AB is equal to CD. Again, the proof is very simple. We know that this equal to this equal to this equal to this because all of them are nothing but the radii. So we have OC is equal to OA, we have OD is equal to OB, all of them being radii, and we have angle COD is equal to angle AOB, which is given. This implies by SAS triangle OCD is congruent to triangle OAB. This implies CD is equal to AB, again by CP, CT, that is corresponding parts of congruent triangles, and so hence prove what we had started off with. Next is another theorem, which is theorem number 3, which states the perpendicular from the center of a circle to a chord bisects the chord. So if this is the center and this was given by O, and this is the perpendicular from the center, and if this was say chord AB, then we have, and say the intersection point is C, we have to prove that AC is equal to CB. The proof can be done like this: joining AO and OB. We know that OCA is also obviously 90 degrees because this is the perpendicular. We have OA is equal to OB because they are radii. You have OC is equal to OC. I mean, this is trivial, or you can call it common. And you know that angle OCA is equal to angle OCB is equal to 90 degrees. So this equal to this, and this is obviously common. So we do not have an SAS condition, but we have something called the RHS condition. So by RHS, or right angle hypotenuse side condition, we have triangle OCA being congruent to triangle OCB. This implies AC is equal to CB, hence proved. Right? Now we will look at theorem number 4, which is simply the converse of theorem number 3. It states the line drawn through the center of a circle to bisect a chord is perpendicular to the chord. Again, we start off by naming the points like the last one. So now we're given that AC is equal to CB, and we have to prove that angle OCA is equal to 90 degrees, which would suffice because OCA, if it is 90 degrees, then OCB is again 90 degrees. It really doesn't make a difference. So we'll start off by joining OA and OB. Right? We know that OA is equal to OB. OA is equal to OB because they are radii, and we are given that AC is equal to CB, which is given, and OC is equal to OC, and that is common. So this implies by SSS we have triangle OCA to be congruent to triangle OCB, right? This implies angle OCA, I'll write that again, angle OCA is equal to angle OCT. We also know that because AB is a straight line, these two form a linear pair of angles. So angle OCA plus angle OCB is equal to 180 degrees. Now replacing OCB by angle OCA, we get 2 angle OCA is equal to 180 degrees. This implies angle OCA is equal to 90 degrees. Hence proved what we had roughly proved. And because angle OCA is equal to angle OCB, we have angle OCB also 90 degrees. So we have proved theorem number 4 also. Next we'll look at theorem number 5. Theorem number 5 states there is one and only one circle passing through 3 given non-collinear points. For the purpose of the proof, let's look at 3 non-collinear points, and we'll call them, say, ABC. A, B, C. Now to check if they actually pass through, they actually lie on a circle, let's join AB and let's join, say, BC, right? And what we'll do is we'll draw the perpendicular bisectors of AB and BC. So we can claim that this is the perpendicular bisector of AB and the perpendicular bisector of BC is something like this. And now because these two are two unique lines, they can intersect only at one point, and let's call that point O. Now because this is the, let's call it line L and this as line M. Now because L is the perpendicular bisector of BC, OB and OC are equal because O is the point lying on L. So this implies OB is equal to OC. And similarly, because O also lies on M and M is the perpendicular bisector of AB, OA is equal to OB. OA is equal to OB. This implies OA is equal to OB is equal to OC. So in a way, we can treat OA, OB and OC as the radii and O as the center and draw a circle which passes through all these 3 points, right? Where these serve as radii. Now, so we have proved that at least one circle passes through 3 non-collinear points. Now we have to prove that it's unique. So the argument for that would be that L and M are two distinct lines, and because they can intersect at max at one point, they do that, and that becomes the center of the only circle that is possible. Hence we have proved that there is one and only one circle passing through 3 given non-collinear points. Now these 3 non-collinear points could well be a part of a triangle, say of a triangle ABC. In that case, the circle which is drawn, on which all these 3 points lie, is called the circumcircle of the triangle ABC. And in turn, the radii OB, OA and OC are called the circumradius. And also the center of this circle which circumscribes the triangle is called the circumcenter. So those are some important terminologies associated with circles circumscribing a triangle. Now there are some more theorems and some more concepts left in this lecture, but we'll pick that up in the next part. For now, this is all. Thank you.